Hello everybody, my name is Swadhin Behera. I am from Japan Agency for Marine Earth Science and Technology. Today I am going to tell you about some of the climate phenomena arising from air-sea interactions in the tropical Pacific and tropical Indian Ocean mostly, but there are other climate phenomena in the Atlantic, in the higher latitudes. I'm not going to cover them. Today I'll just talk about the El Nino Southern Oscillation, its past, its present, and its future. El Nino Southern Oscillation is the most dominant phenomena on Earth, and it has large-scale influences all over the world, influencing the climate and weather, and in that way affecting socio-economy in many parts of the world. For example, you can see there are many extreme events happening over Indonesia, the floods, the droughts. 2023 we have several droughts, heat waves, and then last year we had floods, and these are kind of associated with the two phases of the El Nino Southern Oscillation. One of them is El Nino, when the Eastern Pacific gets warm. We'll come to that in a minute. And the Western Pacific becomes cool, so dry, and then we have droughts and dry condition leading to heat wave and sometimes forest fires. When we have La Nina, the western side of the Pacific is warm, we have a lot of moisture, and then you have a lot of rain and floods. That also affects adversely our society. And related to that, we have also several other socio-economic stresses like disease, water management, agriculture, crop yield, fish yield, etc. So these are some of the climate phenomena, and today we'll mostly cover about the El Nino and La Nina, El Nino Modoki, La Nina Modoki, and the Indian Ocean Dipole. And as you can see here, most of those extreme event years are some way or other linked to one of these climate phenomena. So in other sense, these climate phenomena modulates the extreme events like drought, floods, heat waves, and sometimes forest fire and disasters. The El Nino Southern Oscillation is the dominant phenomena that affects the climate and weather. And the hypothesis of ENSO, how it happens, is largely dependent on several hypotheses. I'll come to that in a minute. But before that, let's see how the climate phenomena, how the air-sea interaction happens in the tropical Pacific because of the air-sea interactions. So you can see here the December, January, February sea surface temperature, the temperature on sea surface. And these are the anomalies. These are the climatology. Once you take the average of 30 years of data, this is for the December, January, February sea surface temperature anomalies. On top of that, we have the surface wind climatology. I'm sorry, not anomalies, climatology. This is surface temperature climatology. On top of that, we have the wind climatology from the surface. Same thing for the June, July, August in the bottom chart. And you can see between December, January, February, and June, July, August, the warm temperature that you see in the tropical region, they shift southwards during December, January, February, and shift northward during June, July, August. And that we know is happening because of the seasonality and the tilt in the axis of rotation of the Earth, 23.5 as you know. So because one hemisphere is exposed to sun more during a particular season, for example, the northern hemisphere is exposed more to the sun in June, July, August. So the high temperature move northward during June, July, August. December, January, February, the southern hemisphere is exposed to sun more, so the high temperature moves southward. This is the north-south movement of temperature, high temperature, dependent on the season, and that season is happening because of the rotation of the axis tilted, the Earth's rotation of the axis tilted by 23.5 degrees. Now, on top of that, you can see that there is also east-west gradient in the temperature, not only north-south gradient. The northernmost latitudes get less sun heat, so those are cooler, and southernmost latitudes they get less sun's energy, so they are also cooler. And tropics get most of the energy, that's why it is warm. We can understand that. The north-south gradient we can understand because of the because of the Earth's position to the sun, relative to the sun. But why you have also east-west gradient? You can see that eastern side of the oceans and the western side of the continents, you get cooler temperature near the coasts compared to what we see on the western side. For example, here Philippine and Indonesian region, you can see the temperature is warm throughout the year, but the eastern side, the South American coast and the Mexican coast and the American coast, you can see that the temperature is cooler compared to what we see near the Philippines and Indonesia. And that happens because of an unique nature of variability coming from the rotation of the Earth. Since Earth is rotating, as you can see, if you see because of the Earth is rotating, if you throw something from the North Pole, it doesn't come directly to the same point at the equator. It turns to the right in the northern hemisphere and to the left in the southern hemisphere, and that is called the Coriolis effect. Because of this Coriolis effect, things rotate in the northern hemisphere and in the southern hemisphere. Just to see the movie how it happens.
An object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by two people on a merry-go-round that spins like the Earth, but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher. Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve away. The direction of apparent motion is to the right when following the path of the ball. Now the ball is thrown the other way. Because the thrower is moving, the ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again.
So this is in principle how the rotation is deflecting the winds in the northern hemisphere to its right. For example, because of this north-south gradient, winds should blow from north to south, because north is cold, south is warm, so always the flow is from colder temperature to warmer temperature. So the wind blows from north to south, but because of the rotation of the Earth, wind rotates, and they rotate to the right in the northern hemisphere. If you see if the winds are coming from northern side to equator, the wind will rotate towards eastern side of the basin. Western side of the basin. So that's why you can see that the winds are already rotated. So trade winds are from northeast from northeast to southwest in the northern hemisphere, and from southwest to northwest, southeast to northwest in the southern hemisphere. So the winds rotate to the right, to the left in the southern hemisphere, and to the right in the northern hemisphere. Because winds are rotating, it creates a transport of water away from the coast, in both hemispheres, to the left in southern hemisphere and to the right in the northern hemisphere. So that's why water is taken away from the coast, and to fill that gap, subsurface water comes up, and that's why subsurface waters are cooler, because the sun's energy are trapped in the surface, and subsurface water is not getting enough energy. That's why subsurface water is cooler. So the cool water comes up, and that's why the eastern side is cooler on these eastern side of the Pacific, and also eastern side of the Atlantic. And these waters are driven away by this wind, and they accumulate in the western side of the Pacific and the western side of the Atlantic, and that's why the western side of the Atlantic and western side of the Pacific are warmer than normal. Indian Ocean has its monsoon wind because of the unique structure of land and sea there. Because land is too much close to the equator, so we get monsoon, the southwesterly monsoon, the winds coming from the southwest to the northeast in the northern summer, June, July, August, and opposite from northeast to southwest in December, January, February. So when the winds are blowing from south to north and rotating slightly towards northeast, these are called southwesterlies because they are coming from southwest. So they drive water away from the coast because the water should be transported to the right in the northern hemisphere. So the water is taken away from the coast, and that's why the Somali region is cooler during summertime and warmer during winter time, because opposite effects. The winds are now southward, so the water is transported to the coast, so the temperature is warmer there. So that's the uniqueness of the Indian Ocean. We'll come to that in my next lecture when we talk about the Indian Ocean dipole. For the time being, we should remember that because of the winds and the trade and the Coriolis effect, the water is transported away from the coast of South America and North America. That's why the coastal region on the eastern side of the Pacific is cooler compared to the western side, and that sets kind of this is the diagram showing you how upwelling happens when the wind is taking away the water from the coast. Upwelling happens and the temperature is cooler. So that's how okay, this is one movie will show you how the upwelling happens through a fish tank experiment.
And that's the demonstration that I'm going to do for you today. Upwelling is where the wind blows across the surface of the ocean. So I've got my fish tank here, which is going to be my ocean. And as the surface water is pushed away by the force of the wind, then the water underneath flows up and takes its place. On the ocean, that's usually the cold, lower ocean water that flows up and takes the place of the warm upper ocean water, or the warm surface water. In this fish tank, the water is all the same temperature, so really you're not going to see warm versus cold or any of that happening. But I am going to try and inject some food coloring, like a nice little bubble of food coloring about the middle before I start this. Okay? Yes, it looks like what? Okay, so I've got food coloring, and Timothy, you can zoom in on that. You can see the bottle of food coloring, Timothy. Pretty much sitting at the bottom. There's a little bit that's mixing at the top, but for the most part, the food coloring is sitting on the bottom. Now what I'm going to do is, I'm going to simulate the wind with my leaf blower. Okay? And hopefully this will work. If this works, what you should see is as the wind is blowing across the surface, the food coloring will actually begin to move up this side and then across the top, because the water will begin mixing.
So